Hello all, for those of you who are following my channel, this will look familiar as we will go over a past paper. The way I do it is I pretty much solve the problems and I provide explanations wherever I can. And whenever I can, I also insert some pieces of theory into the problems and try to tie the context of the problem to the theory and so on. I'm sorry for not uploading for some time now. It's because I am preparing videos for other topics, including quantum mechanics for college and stuff like that. Hopefully this channel will grow to include as many past paper solutions as possible, as well as some theory. And I'm also preparing theory lessons for Unit 1. Hopefully I will start making those videos soon. Anyway, so this is the paper from October 2023, and it's Unit 4, guys, okay? Dealing with further mechanics, fields, and particles. And let's jump straight in. Okay, again, in Section A, there are 10 questions, multiple choice, 1 point each. This question should take you about 1 minute, okay? So usually the rule of thumb is 1 minute per mark, okay? So, question 1. The nucleus of an isotope of osmium contains 76 protons and 190 neutrons. Which of the following can be used to represent this isotope? Okay, OS is the element, so okay, that's correct, and it's the same in all answers. So we have to pretty much sum 190 plus 76. And oh, okay, this is obviously wrong. This is obviously wrong. So the only correct answer is A or B, and it cannot be B because it already has 190 neutrons, so 190 plus 76 is 266 protons and neutrons, so the correct answer is A, okay? Because remember, for an element X, we need the mass number and the number of protons, okay? Mass number up top, top left, bottom left, proton number, okay? Question 2. A car travels along a straight horizontal road. A drag force of 150 newtons acts for 15 seconds, causing the speed of the car to decrease. Which of the following is the change in momentum of the car due to the drag force? Okay, recall that change in momentum is equal to the force times the time for which this force was acting. And this is simply a multiplication. 150 times 15 gives us 2,250 kilograms mass, seconds to the minus 1. Correct answer is C. Okay, simple problem. Question 3. The tubes of a linear accelerator LINAC get progressively longer along the length of the LINAC. Which of the following is the reason for this? Okay, A, the frequency of the applied potential difference decreases. This is obviously wrong because the frequency of the potential is constant. The frequency of the applied potential difference increases, also wrong since it's constant. The particles gain mass as they accelerate. They do, but it's irrelevant to this question. And then D, the particles must spend the same time in each tube, which is the correct answer. And they have to spend the same time because the frequency of the applied voltage is the same, okay, in each tube. But the velocity changes. So since the velocity increases, we have to increase the length of the tube, so the time they spend in the tube is the same, okay? Question 4. Which of the following is a possible unit for magnetic flux? Okay, magnetic flux is magnetic flux density times area, right? And if we try to work on the units, and I use square brackets whenever I'm referring to the units of a certain physical quantity. So phi, the flux, is the units for flux are the units for B and the units for A, which is, and the units for magnetic flux density is Teslas, for area is meter squared, so it's the correct answer is A. Right, 5. Which of the following is not a valid conclusion from Rutherford's alpha particle scattering experiments? All right, the nucleus contains most of the mass of the atom. which is a valid conclusion. Okay. B, the nucleus contains protons and neutrons. Okay. It's pretty much this, because they didn't know about the neutron at the time of Rutherford. So it's B. But let's go over the other answers. The nucleus is charged. This is something they concluded. Okay, so that's correct. And then the nucleus is very small compared with the atom, which is something they concluded as well. So the only thing they didn't conclude from these experiments at the time was the existence of neutrons. And for those of you who are into history, now I'm in trouble because I don't have my notes in front of me, but this kind of thing was discovered by Rutherford in the 1910s, okay? Whereas the neutron was discovered in the 1930s. Okay, if I had to put an exact date, I think it was 1913 for the Rutherford experiment and 1932 for the neutron discovery. Check Wikipedia, I don't know. Ask ChatGPT. I don't have my notes in front of me, so I'm doing this on the fly, something like that. So, question 6. A particle detector shows tracks produced by two particles X and Y. The particles were created by the decay of a kaon at point O. Which of the following can be concluded from the tracks? Okay. Now, option A, a magnetic field acts into the page. So if it acts into the page, we cannot conclude anything from this because we don't know. We don't know the charges of X and Y, so it doesn't matter if it's in or out. So X is a positively charged particle. There is no way to figure this out because we don't know the direction of the magnetic field. Y is an electron. It can be, but we don't know. And then part D is the most suitable candidate. X and Y have opposite charge, which is the correct answer. Okay, and the reason is that irrespective of whether the magnetic field points in or out, this is positive and this is negative, or the other way around. Okay, and this is a diagram that shows pair creation pretty much. Okay, so these two particles are the same. It can be a proton and an antiproton, an electron and a positron, etc. Okay, so the correct answer is D. 7. The diagram shows the paths of two charged particles X and Y moving at the same speed in a uniform magnetic field. Okay. Which row of the table describes the properties of Y compared with the properties of X? Okay, this is a little bit involved. So let's do one simple kind of calculation. So for a charged particle traveling with some speed v in a magnetic field, the force QVB is acting on it, which becomes the centripetal force. So mv squared over r is the angular acceleration, right? The centripetal force, I'm sorry. So this v cancels, and then we can solve for r, and we find mv over qb. Okay, so this is going to help because this radius is much smaller, so this is the radius, whereas for this one the radius is something like this. Okay, so for x, so rx is larger than ry. This is going to help with a lot of the options here. So is the mass of y greater than, so okay, what does it say? Mass of y is greater than the mass of x, and charge of y is the same as charge of y. If that was the case, so the mass of y would lead y to have a larger radius, so that's not correct. Okay, now b, the mass of y is less than the mass of x. Okay, it could be, and then it says that the charge of y is greater than the charge of x. Okay, that's a possible answer, right? Because that will lead to a smaller radius, so ry will be less than x. And in fact, I think, yeah, this is the answer, B. Because then for C, it says the mass of y is the same as the mass of x, and the charge of y is less than the charge of x. That would lead y to have a larger radius, so that's wrong. And then the mass of y is greater than the mass of x, and the charge of y is less than the charge of x. That will lead y to have a larger radius, so that's wrong. So yeah, B is the correct answer, guys. Okay, let's go to 8. Okay, you see this took us a few minutes, maybe 2 or 3 minutes. If this happens in a test, you shouldn't panic. Just take into account that some questions are harder than others, okay? So that's fine. Question 8. A toy aeroplane is traveling in a circular path. The toy aeroplane completes 12 revolutions in 6 seconds. Which of the following gives the angular velocity in radians per second of the toy aeroplane? Okay, this is simple. Okay, we are given 12 revolutions, so 2 pi is 1 revolution times 12, because it's 12 revolutions in 6 seconds. Remember that omega is theta, the change in theta over the change in time. Okay, so this is what I did here, and the correct answer is B. Okay. Question 9. A capacitor discharges through a resistor. The time constant of the circuit is 5 seconds. What is the time taken in seconds for the charge on the plates of the capacitors to halve? Okay, we need to find T1 half, pretty much, the half-life, right? Which is equal to T times ln of 2, where tau, not T, tau, I'm sorry, tau is the time constant, okay? So the time constant is 5, and then the half-life is given by this expression, and I think this should be in the back of your paper. Let's go check. They give you some formulas. So let me check. So unit 4, okay. Do you see, do they give this? Okay, no, I'm not sure. They don't. Okay, so in case you forgot this, I'm gonna show you how to prove it. I'm sorry, let's go back. So here was the problem. Okay, so the way to find it in case you forgot it is to use Q. Charge remaining is the initial charge times E to the minus T over the time constant, and to find the half-life you need to assume that half the charge is gone, so you substitute Q naught over 2 on the left hand side, and on the right hand side you are left with E to the minus T1 half, which is the half-life over tau, and if you work the math out you will find that T1 half is tau times ln of 2. In any case, the correct answer is D. Okay. If this didn't make sense, ask me in the comments and I will provide more details. Okay. Now, question 10. A car travels over a humpback bridge as shown. The bridge forms part of a circle of radius r. Okay. The car has mass m and travels with constant speed v. The car is at the top of the bridge. Which of the following expressions gives the force from the bridge on the moving car? Okay, so this undergoes a circular motion. Okay, this is the circular motion and this is the radius r. Okay, how many forces are acting on this car at the top? The normal force from the ground and its mass, correct? And we need to find the force from the bridge. So we need to find N. Okay, so we need the force. We need the total force that points inwards in this direction to be equal to the centripetal force, right? In order to have circular motion, okay? So that's the rule. So the total force has to be mv squared over r. Therefore, we need mg minus n to be equal to mv squared over r. And the reason is that mg has to be larger than n, otherwise it's going to fly off, okay? Therefore, n is just mg minus mv squared over r. And this way, the car will not fly off, and the correct answer is C. Okay, moving on. The photograph shows children. We're into section B. I'm sorry, I forgot to mention that. And let's work on problem 11. The photograph shows children on a roundabout in a playground. I used to love this when I was a kid. I used to run like a crazy person, spinning that thing, and then I was jumping while it was still spinning, and I was jumping on that, and I was holding as hard as I could on the bar there, and I don't know, I was a crazy kid. So the roundabout is a flat platform with bars. The children make the platform rotate by running on the ground whilst pushing on the bars. It takes 12 seconds for the roundabout to make 2 complete rotations. A child is standing on the platform 1.8 meters from the center of the roundabout. Calculate the speed of the child. Okay, so the linear velocity of an object, in this case the child, I'm sorry, okay, the linear velocity is omega, the angular velocity, times the radius, okay? And omega can be found by this information over here, okay? So it says 2 complete rotations in 12 seconds. Remember that omega is delta theta over delta t. Delta theta is 2 pi. By the way, when we work with circular motion problems, we use radians, okay? So 2 pi times 2 revolutions, right? And this takes 12 seconds, right? Times 1.8 meters for the child gives us 1.89. Oops. Gives us 1.89 meters per second. And this should be the easiest 3 marks you should snatch from a paper like this, okay? I mean, this is an easy problem. So let's move on. Question 12. An electron has kinetic energy 7.2 times 10 to the negative 16 joules. Calculate the de Broglie wavelength of the electron. Okay, so let's write down 2 equations that we will need. Okay, we need to calculate the de Broglie, Prince de Broglie wavelength, and the expression is h, Planck's constant, over the momentum p. And then we are given the kinetic energy, so it's good to use this formula for the kinetic energy, p squared over 2m. It's going to allow us to plug in things easily. So p is the square root of 2m times the kinetic energy. And if we plug into lambda, we find h over the square root of 2me. And then h, I know it by heart, but you should consult the back of your paper. 6.63 times 10 to the negative 34 over the square root of 2 times 9.1 times 10 to the negative 31 times the kinetic energy, which is given as 7.2 times 10 to the negative 16 joules, okay? And this yields 1.83 times 10 to the negative 11 meters. One small remark here, the energy is given in joules. If it was given in electron volts, you have to convert to joules, because remember, all units have to be converted to base units, and base units are kilograms, meters, seconds, kelvins, amperes, and there are 2 more, the candela and the mole, okay? So everything has to be converted to this. So if you're given an energy in electron volts, it has to be converted to joules, because joules is kilograms times meter squared over second squared, okay? And this is all I wanted to say, I guess, okay? Don't forget to convert to base units. You didn't need it here, but you might need it in future problems, okay? So let's erase this because it's irrelevant. It's not irrelevant. I mean, it's not related to the problem. So question 13. A student clamped a metal rod horizontally in a uniform magnetic field as shown. The student connected the ends of the metal rod to a power supply, an ammeter, and a switch in a series circuit. When the student closed the switch, there was a current in the metal rod. Okay. When the switch was closed, the reading on the balance increased by 2.8 grams. The reading on the ammeter was 3.6 amperes. The flux density of the magnetic field was 120 milliteslas, and the length of the rod in the magnetic field was L. Calculate L. All right, so in this case, we pretty much have the creation of a force due to a current passing through a magnetic field, and the force is F Bill, remember that? Okay, which points up pretty much, okay? And then you have the mass of the cable pushing down, okay? And these two have to be equal, and that's it, okay? Yeah, that's it. So this has to be equal to mg. So we have to solve for L, which is mg over bi. So 2.8 times 10 to the negative 3 grams. Remember, 1 gram is 10 to the negative 3 kilograms, okay? Times 9.81 over the magnetic field, which is 180 milliteslas, times 3.6 amperes, yields 0.064 meters, which is the answer. Okay, next question. A car traveled in a circular path as shown. Okay, and the view is from above. Okay, a passenger in the car made the following claim. When the car was traveling at high speed around the circular path, I was thrown outwards due to a force acting on me. The outward force acting on me was the centrifugal force. Assess the claim made by the passenger, and this is a question for 4 marks. Okay, so 4 marks means that you have to give about 3 and 4, ideally 4 arguments to either support the claim or dispute it. Okay, so so the car moves in a circular motion because a force is acting on it. If the force was not acting on it, it will move on a straight line. Okay, the force is inwards. And plays the role of the centripetal force. Okay, the inward force is exerted by the car on the passenger. There is no outwards force hence the claim is false. Is false. Okay, the centrifugal force mentioned is a fictitious force, it's not a real force. Okay, the only real force is the centripetal that acts inwards. Okay, and the passenger is wrong. So let's move to the next question. The nuclear model of the atom was developed after a series of experiments in which alpha particles were directed at a thin gold foil. An alpha particle that has, which is pretty much a helium-4 nucleus. Okay, so an alpha particle with kinetic energy 5.52 MeVs approaches a gold nucleus head-on as shown, and we are given the mass number and the proton number for gold. Okay, the alpha particle is brought to rest and then returns along its original path. Calculate the minimum distance between the alpha particle and the gold nucleus. Okay, so pretty much the alpha particle has some kinetic energy, right? And it's positively charged. And this is also positively charged, okay? So at some point, all the kinetic energy will be converted to potential energy, right? The potential, the electromagnetic repulsion between these two guys is gonna make the alpha particle stop and then return. So at the point of minimum approach, all the kinetic energy of the alpha particle will be converted to potential energy. So the kinetic energy, in other words, of the alpha particle, okay, will be converted to potential energy, which is equal to K times Q1 times Q2 over R squared. And this R is what we are looking to, over R, I'm sorry. Sorry about that. It will be R squared if it was the Coulomb's law, okay, if it was a force. We are looking for an energy here, so it's over R. So R is K Q1 Q2 over E. And if we plug in numbers, K is equal to 8.99 times 10 to the 9 times 79, which is the atomic number of gold, times 2 for the charge of the alpha particle, and times 1.6 times 10 to the negative 19 coulombs squared, which is the charge of one electron, over the kinetic energy, which should be converted to joules. How do we do that? So 5.52 MeVs, so times 10 to the 6 to convert to EVs, and then 1 electron volt is 1.6 times 10 to the negative 19 joules. How do I know this? Because 1 electron volt is the energy that one electron that gets accelerated through a potential of 1 volt. What am I saying? 1 electron volt is the energy of 1 electron in a 1 volt potential. Okay, that's it. So if we work this out, we get 4.11 times 10 to the negative 14 meters. Okay, so they come pretty close because remember the dimensions of a nucleus is about 10 to the minus 15 meters. So they come really, really close. Okay. Now B. An alpha particle with a different energy approaches the gold nucleus. The minimum distance between this alpha particle and the gold nucleus is 5.68 times 10 to the negative 14 meters. Calculate the maximum electrostatic force F that acts between this alpha particle and the gold nucleus, okay? So now we need the force, okay? The mistake I made earlier, remember? So the force is K Q1 Q2 over R squared. So K is 8.99 times 10 to the 9. And then we have 79 times 2 times the charge squared over the distance 5.68 times 10 to the negative 14 squared. And if we work this out, we find 11.27 newtons. So about 11.3 newtons. which is a huge force, guys. We are talking about subatomic particles with masses at the order of magnitude of 10 to the minus 27 kilograms. So something so tiny like that exerts a force, due to its charge, of course, exerts a force of 11 newtons. So 11 newtons is, if we have 1 kilogram, okay, the weight of 1 kilogram is 10 newtons. So something like that, okay, a force like that by particles that are billions and billions of times lighter than us. So that's crazy, okay? That's something to think about. Now, let's move to the next question. Okay, this is a long writing problem due to the asterisk, okay? Yes, okay, and usually these problems are 6 marks. A bar magnet was dropped vertically through a small coil as shown. Okay, and we have the coil and everything. The coil was attached to a data logger. The data logger recorded the variation of EMF across the coil with time. Okay, and we have this beautiful graph. Okay, the output is shown below with respect to time. All right, explain the variation of EMF with time. Let me see. All right, so explain. Okay, I have to edit this part out. All right, we have to explain the variation of EMF with time. So let's see. So first we have an increase and then a decrease. So let's see. So the change, the way to answer this is that the change in flux linkage, and remember flux linkage is given by n, the number of turns, times the flux in each turn, okay, induces an EMF, okay? The greater the change, the larger the EMF. When the south pole okay, let me show you the scheme. So when the south pole, so this pole, okay, reaches the coil, the flux reduces, and it's such that and the induced EMF is such that as to produce a current that opposes the change in EMF. As the south pole passes through the coil, the EMF is negative, this part over here, okay? The EMF is negative as the speed of the magnet decreases. So to summarize, As the magnet enters the coil, the flux increases, therefore it induces an EMF, okay? And the EMF is such that this coil creates a current pointing this way so as to create a magnetic field that points in the opposite direction. So it wants to kind of annihilate the North Pole, pretty much, okay? And then when it exits, so when the bar magnet comes here, for example, it tries to exit, now the current flows in the opposite direction, okay? So in this direction now, this direction, okay? No, this direction, sorry. So that it produces a North Pole that is gonna pull the South Pole back up, if that makes sense, because the induced current always opposes the reason why it was created. So the reason why this current was created was the fact that the magnetic flux is reducing as the magnet leaves, pretty much. So it wants to pull it back, pretty much, okay? Hope this makes sense. So let's move on. Problem 17. A copper rod PQ is moved with velocity v along a pair of copper rails as shown. The rails are a distance d apart, okay? So as the rod moves through the magnetic field, it cuts the line, therefore we expect some EMF to be generated, right? Due to Lenz's law. So the rod and rails are in a uniform magnetic field that is directed vertically downwards, okay? Calculate the EMF induced across the copper rod. And we are given the magnetic flux density, the velocity of the rod, and the distance between the rods. So this distance, okay. Between the copper rails, pretty much, I'm sorry. Okay, so let's start from the basics. The M is given by the change in magnetic flux with respect to time. And the magnetic flux is given by B times A. I'm sorry, this should be a delta over time. In this case, we don't have a coil, so N is 1 pretty much, because some of you will say this should be N, B, A, but in this case, N is 1, okay? So let's erase that. Then recall that the area is given by, okay, B is constant, so it gets out of the delta. So the delta acts sort of like a derivative, right? So B is constant. And then what is the area? The area is pretty much D, right? Sorry. It's D times X, where X should start from here, okay? So X is how much distance it covered in this magnetic field, okay? So X times D gives you the surface area cut by this copper rod as it moves through the magnetic field. So B gets out, and then we have delta of D times X over delta T, but then D is constant as well. The only thing that changes is X, the distance it covered through these rails. So we are left with minus Bx and then delta D, sorry, B, D and then delta X over delta T, which is the velocity, right? So we have minus B d V, and we are given everything. We have to convert milliteslas into Teslas, so we have 150 times 10 to the negative 3 Teslas. The velocity is given in meters per second, so that's fine. And we have to convert D into meters, which is 7.5 times 10 to the negative 2 meters. And if we plug the numbers in, we get 3.94 times 10 to the negative 4 volts, actually minus, but you have to drop the minus, doesn't matter in this problem. We are just asked for the value of the EMF. So 3.94 times 10 to the minus 4 volts. Explain the direction of the induced EMF. Okay. All right, so Lenz's law says that the induced EMF must oppose the reason. I'm sorry for my bad handwriting. Let me make, okay. The reason that created it. And the reason that created this EMF is the rod cutting through the magnetic field, okay? So we basically have to make the argument that when the rod attempts to enter this magnetic field, the magnetic field is going to induce an EMF, and therefore a current that is going to oppose this change. Therefore, it's going to induce a force to the right. Okay, so a force to the right means that we need a current that runs from P to Q, pretty much. Okay, so plus and minus. Okay, so the current should flow this way. Okay, is that correct? Wait, I'm confused now. I'm sorry, give me a second. So basically we have to have a current that creates a magnetic field that goes out of the page. Okay, so the current has to flow from Q to P. Okay, which means that this is the negative and this is the positive. Okay, so and that's the answer. Okay, and we ask for the direction of the induced EMF, which is kind of weird, but that's the argument. Okay, so you can also write here that a current has to run through the rod such that it creates a B out of the page. And the reason is that, recall, I'm gonna draw it here. So if we have a current running in a loop this way, okay, this current creates a magnetic field out of the page. And if we have a current that flows this way inside the loop, okay, it creates a magnetic field into the page. Okay, I hope this makes sense. So in our case, we need the current to flow this way so that it creates a magnetic field out of the page. Okay, I hope this makes sense. So let's move on. Question 18. A student used the circuit shown to determine the capacitance of a capacitor. All right. The student connected the switch to X to charge the capacitor. So the switch was this way. Therefore, okay, we have the voltage that charges the capacitor. Okay, that makes sense. She then connected the switch to Y so that the capacitor discharged. Okay, so then she changed the switch to Y so that the capacitor discharged through the 150 kilo ohm resistor. The student started a stopwatch when she connected the switch to Y, okay, and recorded the voltmeter reading V every 20 seconds as the capacitor discharged. The graph shows V varied with time t. Okay, and here we have to recall that V is V naught e to the minus t over tau, where tau is the time constant. Okay, and the time constant is the time needed for the initial voltage to drop to 37%. Okay, and 37% is the value of 1 over E, which is 1.271, which is 0.37. Okay, now question A. The capacitor is labeled as 470 microfarads with a tolerance of plus or minus 10%. Evaluate whether the capacitance of the capacitor is within the stated tolerance. Okay, so we pretty much have to calculate tau in this problem. Okay, so we have to find what V naught is. We have to calculate tau from the graph so that we can find C because R is given. Okay, so recall that tau, the time constant, is R times C. And how can we find that? It's the time needed for the initial voltage to drop to 37%, right? So what's the initial voltage? So we have 5, that's 7.5. So 12, so about 12 volts is the initial voltage. Okay, so V naught is 12 volts, and 37% of that is 4.44 volts. Okay, how much time did it pass until the voltage drops to 4.44? Let's go to the graph. So something like that. Okay, so that's about 4.5. So tau is about 70, and the time scale is seconds. Okay, be careful with that because sometimes they might have it as milliseconds or so and so on. So be careful with that. Okay, 70 seconds, but tau is R times C. So C is 70 seconds over 150,000 ohms, which gives you 467.8 microfarads. And the capacitor is labeled as 470 microfarads with a tolerance of plus or minus 10%, which means that the capacitor labeled, okay, let's call it L, is 470 plus or minus 10% of 470, which is 47, right? Microfarads. And 467 is definitely within the limit, so that's true. Okay, so the capacitor is within the stated tolerance. Now, question B. An ultracapacitor is a high capacity capacitor. Okay, one ultracapacitor has a capacitance of 47 farads. That's huge. The maximum charge this capacitor can store is 56 coulombs. It is suggested that this capacitor could store 1,000 times as much energy as a 470 microfarads capacitor charged to a potential difference of 12 volts. Assess the validity of this suggestion. Okay, this is a simple application of the energy stored in a capacitor, okay? And there are various formulas for that, which are all equivalent. So Q squared over C is one of them. And then also 1/2 CV squared and 1/2 QV. I bet all these formulas are in the back of your paper. Let's go see. Okay, we need unit 4. Here it is. And yes, this is the energy stored in a capacitor, okay? So you're given all the formulas you need over there, okay? Let's go back to our problem. We are here. Let's close this. Let's actually erase what we don't need. So for the ultracapacitor, we need 1/2, and we need to store 56 coulombs squared over 47, and that's 33.36 joules. And from our normal capacitor, let's name this U, okay? We have 1/2, let's use CV squared now because we are given the voltage and the capacitance, okay? So 1/2 470 times 10 to the negative 6 times 12 squared. That's 0.034 joules. And if we divide the energy that the ultra capacitor can store with the energy that the normal capacitor can store, we find the number 986. So the statement is approximately true, okay? Because 986 is close to 1000. And this reminded me of an old joke in theoretical physics, actually. So in theoretical physics, the claim is that 2 is equal to pi is equal to the square root of 2 is equal to the imaginary unit, I think, sometimes, and it's equal to 1, okay? So all these numbers are 1, which is a joke, okay? That's not true. But in physics, I mean, we make approximations, so that's fine. Now, let's move to the next question, which is, from the looks of it, it's a momentum conservation problem, okay? So let's see. Curling is a sport played on ice, and Canada, from what I know, is one of the best countries in the world in this sport, which kind of makes sense because it's far north, it's cold, and so on. So, players slide stones made of granite along the ice. The photograph shows 2 of the stones. Each stone has a mass of 19.1 kilograms. Okay, so this involves collisions between equal masses, which is always nice. A player slides a stone at the velocity of 1.7 meters per second towards a stationary stone as shown below. The stones collide. After the collision, both stones move off as shown below. Okay, show that V is about 1.3 meters per second. Okay, so this is V, right? Okay, I'm gonna try to make it as easy as possible. So this is the before situation, and we have momentum only in the x-axis, okay, equal to the mass of the stone times this velocity. So that's the momentum before, and then the momentum after. So this is the after situation. So in the after situation, we have a momentum in the x direction, which comes from the addition of the component related to this velocity and the component related to the other velocity. I hope this makes sense. But the trick here is to recognize that in the y direction, before the collision, there was no motion. Okay, so after the collision, this component of the momentum, which is going to be 0.87, which is the velocity, times, so 19.1 kilograms, which is the mass, so m times v, let's call it v1 because v is the other velocity, okay, times sine of 50, okay, should be equal to this component, which is nothing but 19.1 times v times sine of 30 degrees, okay? So let's write that down. M times 0.87 times sine of 50 is equal to m times v times sine of 30, and the masses cancel. This is what I meant when I said that when you have a momentum and collision and stuff like that, and the masses involved are equal, you always get nice simplifications. So v is 0.87 times sine of 50 over sine of 30. And if we do the calculation, we find 1.33 actually meters per second, which is about equal to 1.3 meters per second. So case solved. Part B, deduce whether the collision was elastic. Your answer should include a calculation. All right, we basically have to find the total kinetic energy before, what's the total kinetic energy before? It's simply 1/2 m, let's write k b, which means k before, 1/2 m v squared v before squared. Okay, so we have 1/2 times 19.1 times 1.7 squared. The other mass is stationary, so it has no kinetic energy, so 2.76 joules. And then, sorry, 27.6, I'm sorry, 27.6 joules. And after we have both masses moving, so we have 1/2 times 19.1 times 0.87 squared plus 1/2 19.1 times 1.33 squared. And if we do the calculation, we find 24.1 joules. So not elastic, because some energy is lost in the collision, probably due to sound, heat, etc. I want to raise a point here. I often see students using sines and cosines when they work with kinetic energy. No, that's a mistake, okay? Because for kinetic energy, the only thing that matters is the value, the magnitude of the velocity, okay? So here we know all the velocities, both before and after, so we can just do a simple calculation and find the kinetic energy. All right, question 20. This looks fancy. In the 18th century, a scientist called Gordon, I've never heard of him, okay, made the first device that used electrostatic forces to produce continuous motion. And demonstration of the principle of Gordon's device is shown. So we have a light conducting sphere of radius r suspended from an insulating thread between two parallel metal plates. A large potential difference V is applied between the plates. Okay. There is an electrostatic force on the sphere when the sphere is charged. The capacitance C of the sphere is given by this formula. This is for those of you who are going to go on to study physics or electrical engineering or anything related to electromagnetics. They will, at some point in their studies, they will have to prove this formula for spherical capacitors, okay? But it's a famous formula in electrostatics and electromagnetics in general. So anyway, let's close the parentheses. So the capacitance is given by that, where R is the radius of the conducting sphere. The sphere is charged by touching it onto one of the plates. The plates are a distance d apart, okay? Calculate the electrostatic force exerted on the sphere. So the first step is to actually find, let's find the capacitance, okay? So C, because you're given the voltage and other constants there, and I'm gonna show you what you have to do. So, but let's find the capacitance. So 4 pi epsilon naught times R, and you can go in the back of your paper and find, so if you go over here, you're given epsilon naught here, okay? And then you multiply by 4 pi, and then for R, we have to convert to meters because R is in centimeters, so 3.5 times 10 to the negative 2 meters is what we have to use. Anyway, if we plug in, we find 3.89 picofarads, okay? And I remind you that picofarads is 10 to the minus 12. Now, the charge, if the voltage is 4,500 volts, if we multiply C by V, let me actually do it, times, I have my calculator here in front of me, okay, we find 1.75 times 10 to the negative 8 coulombs, okay, that's the charge. on this sphere, okay? And then we have to find the electric field. Remember that the electric field, this electric field between these two plates, we're given the distance between the plates, okay? And we know the voltage, so we can use V over D, which is also in the back of your paper, I'm pretty sure. But let's verify the claim again. This one, okay? For this only applies to parallel plates, guys, okay? Don't get confused. That formula is only used for parallel plates. Okay, let's go back to the problem over here. So we can calculate the electric field as 90,000 volts, newtons per coulomb. And recall that the force, if you know the electric field and the charge, the force on the sphere from the plates is going to be Q, the charge on the spherical capacitor, times the electric field. And if you do this multiplication, you find 1.58 times 10 to the negative 3 newtons. Okay, this was a little bit involved, but even if I didn't know anything about the problem, I just used formulas given to us, okay? So we're given the capacitance, so we can calculate the formula for the capacitance, so we can calculate the capacitance. Then we can just find the charge on the capacitor using the familiar formula CV, okay? And then since you are given the distance between the plates and the voltage, you can calculate the electric field between the plates. And then just by using Q times E, we can find the force, okay? So even if you don't know anything about the problem, you can kind of work your way around this problem just by using common sense and the formulas from the back of the paper. Anyway, part B. After the sphere has been charged, the sphere starts to oscillate between the plates. The sphere touches each plate alternately, okay? Explain why the conducting sphere oscillates between the two plates. So the answer here is kind of simple. So when it touches the negative plate, the sphere becomes negative, right? Due to the conduction of electrons onto the sphere, pretty much, okay? So the sphere becomes negative and repelled, and therefore gets repelled by the negative plate. Okay, and attracted to the positive plate. Okay, it then becomes positive, gets repelled and attracted back to the negative plate, and so on, okay? So this lasts forever, okay? Not forever, I mean eventually it's gonna stop because we have friction, so we will have a loss of charge, a loss of potential, and so on. I mean, a perpetual machine was never devised in the history of humanity, and I bet it will never be devised. Okay, this is a bold claim, I know, but a perpetual machine involves violating the law of conservation of energy pretty much, so no. All right, part C. A few years later, another scientist called Franklin adopted Gordon's device. Franklin suspended a conducting sphere between two metal bells. One metal bell was connected to Earth, okay, this one, and the other metal bell was connected to a lightning conductor as shown. During an electrical storm, the sphere oscillates between the bells and the bell's ring. Okay, electrical storm. Okay. The lightning conductor is a long wire attached to the top of a building. The lightning conductor becomes positively charged when in an electric field. The conducting sphere is initially uncharged. Explain why the conducting sphere starts to move between the bells during an electrical storm. Okay. Let me see. So basically, okay, so the reason is that this will create a similar situation to the metal plate. So the bells act as two parallel metal plates. Okay, once the bell connected to the lightning rod gets positively charged, the electrons on the sphere, okay, so basically this is going to be positively charged, therefore the electrons will get concentrated, yes, on the surface of the sphere, right? And the sphere is going to be attracted to the positive bell pretty much, okay? And then it's going to touch it, and then it's going to get positively charged and then oscillate back and forth as we discussed in part B. Okay, so let's finish this. Positively charged. The electrons on, okay. The electrons on the sphere will move to the side facing the bell. Get attracted. So the sphere moves towards the positively charged bell, touches it, and then it starts oscillating. And that's the answer. That's a good answer for this problem. It's a 2-mark question, so it's kind of a simple problem. Okay. Let's move to the next problem. This is a long paper, guys. I mean, this was an unusual situation. We are already to question 21. They usually have about 19, 20 questions. So anyway, question 21, pions are created in the upper atmosphere when high energy cosmic rays interact with nuclei. Pions are mesons and they quickly decay to muons. Muons are leptons with a mass of 106 MeV over c squared. Give a possible quark structure of a pion. So recall that, is it mentioned anyway? Okay, mesons consist of a quark and an antiquark, right? So pions are first generation mesons, okay? So they were the first to be discovered, and the first generation of leptons where of quarks where the U and the D's, right? So a possible quark structure for a pion could be U D bar or U bar D, where the bar means the anti-U, okay, or the anti-D. Or it can be U bar or D bar, okay? Yeah, there is nothing else to say here. It's a 1 mark question, so it's an easy problem. Let's move on. The equation shows a pion decaying into a muon and an anti-neutrino. Energy and momentum must be conserved in this decay. Explain two other conservation laws that apply to this decay. Okay, so we need to have a conservation of charge. Conservation of charge. And do we have that? We do, because we have pi minus, which has a charge of -1, decaying into a negative muon, negatively charged muon with charge -1. So we have conservation of charge. We also have conservation of lepton number. Okay, what am I talking about? The lepton number before is 0 because the pion is not a lepton. Only leptons can have a lepton number. But then the lepton number for the muon plus the neutrino is also 0. It's -1 for the, it's +1 for the muon, -1 for the muon anti-neutrino, okay? So it's also 0. And they are asking for two conservation laws. Another one you can mention is the conservation of baryon number. And this is simply true because the pion has a 0 baryon number because it's not a baryon. And then the muon and the neutrino also have a baryon number of 0 since they are not baryons, they are leptons. Okay, so there you go. Then question C, calculate the mass in kilograms of a muon. Okay, so we are given that the mass of the muon is 106 MeVs over c squared. So this is just a simple calculation. So we have 106 times 10 to the 6 EVs over c, and c is 3 times 10 to the 8, and the whole thing has to be squared. And then recall that 1 EV is 1.6 times 10 to the negative 19 joules over c squared yields 1.88 times 10 to the negative 28 kilograms. And let me show you that the units work out fine because we have joules divided by speed squared, which has units of meter squared, c squared. And I remind you that 1 joule is 1 kilogram times meter squared over second squared. So the meters and the seconds get cancelled. So we are left with kilograms. And how do I know that 1 joule has units of 1 kilogram times meters squared over second squared? Simply by remembering that the kinetic energy is 1/2 mv squared. So in terms of units, we get kilograms for the mass times meter squared over second squared. So that's it, okay? Right, is there more to this? Yes, there is. When at rest, pions have an average lifetime of 26 nanoseconds. When produced in the upper atmosphere, high energy pions have a speed of up to 99% the speed of light. Explain how the average lifetime of these high energy pions compares with the lifetime of pions at rest. You do not need to carry out any calculations. So so for moving pions, the lifetime gets longer due to time dilation. Okay, so moving objects move slower pretty much. Sorry, the time moves slower for moving objects. Okay, so the lifetime of high energy pions is larger than the lifetime of stationary pions, and that's the answer. Okay, for those of you who are going to study physics, this is a bonus answer, and it's out of scope. This is not something you need to know for the A levels, but to find that time, you actually you can actually use this. The lifetime for the moving pions is equal to gamma times tau, and tau is simply 26 times 10 to the negative 9 seconds, and gamma is this factor 1 minus 0.99 c over c squared. Okay, this is from Einstein, so the lifetime of the moving pions would be 1.84 times 10 to the negative 7 seconds. Okay, so this is a bonus. Again, I'm gonna put it here and say that this is out of scope for high school students. Okay, this is scary physics. It's not scary, it's kind of simple actually. I mean, special relativity, you cannot say it's simple, but it's understandable. General relativity is harder, but for those of you who are going to study physics, that's the actual answer. So, but I'm going to erase it because you don't need to know this. All right. And I think this should be the last one. Okay, yes. So, question 22. The electron beam tube can be used to determine the specific charge E over m of an electron. The potential difference V is applied between the cathode and the anode to produce a beam of electrons. Okay, the beam is aimed at a fluorescent screen. Okay, inside the tube, and the path of the electrons is seen on the screen. There are two parallel metal plates above and below the screen. A and B are connected to these plates and allow a potential difference to be applied across the plates. Explain why electrons are deflected into a parabolic path when a potential difference is applied between A and B. And the reason is because they get attracted, I guess, right? So how do we answer this? Let's say that this is a plus and this is a minus. You will have electrons exiting the anode there, so therefore they're gonna be moving like that in a parabolic path. And the reason is that if you have a voltage across A and B, then you will have an electric field equal to V over D generated between the plates, right? We discussed this in a previous problem. Okay, therefore the electrons are going to experience a force Q times E, and the charge of one electron is simply E times V over D, and this force is going to act along the y-axis, right? The force is going to be in this direction. Okay, so this is the force. There will be no force in the x direction, only in the y direction. Okay, therefore, due to Newton's second law, an acceleration will be experienced by electrons in the y direction. So we will have F is equal to ma, and m is the mass of one electron times the acceleration. And this will be E v over d. So the acceleration is q times, the acceleration is E v over me times d. Okay, and in the y direction we will have, remember the Suvat equations from back in the day from unit 1. So s is given by the initial velocity times t plus 1/2 a t squared. Okay, and this is a parabola, guys. I mean, this part is a parabola, and I think that answers it. Okay, part B. A potential difference V of 850 volts is applied between the cathode and the anode. Show that the maximum speed of the electrons as they emerge from the anode is about 1.7 times 1.7 times 10 to the 7 meters per second. Okay, and here they are talking about this voltage. Okay, so this voltage is different from this voltage. So we can say that, remember that the energy of some charge inside some potential difference is simply Q times V, right? So the potential difference is this, and the charge is the charge of one electron, and this should be equal to 1/2 times the mass of the electron times the velocity squared. Okay, I made the V look like a voltage on the left-hand side. So if we solve for V, we find 2 times the charge of one electron times that voltage over the mass of one electron. And if you plug numbers in, you will find 1.73 times 10 to the 7 meters per second. Really close to what they are asking. Okay. Now, part 2, the electric field strength between the parallel metal plates is 1.7 times 10 to the 4 volts per meter. Okay. The length of each plate is 7.5 centimeters. The electrons pass through the region between the parallel metal plates. So they are talking about this region now, this one. Okay. Okay. Calculate the vertical deflection of the electron beam. You should ignore the weight of the electrons. Okay. So the first step is to calculate the acceleration. Okay. So the acceleration, we did this earlier. Okay. In our case, we used EV over D, so we're going to replace this with E because we are given E. Okay, so the acceleration is simply E times the electric field over the mass of one electron. So the acceleration is 2.99 times 10 to the 15 meters per second. Second squared, I'm sorry. Now the horizontal, let me see, pass through the region between the parallel plates. Okay, so horizontally, so these are the plates, right? So we need to find for how long these electrons were present in this electric field. And we can find that by knowing that the initial velocity u is what we calculated earlier, 1.73 times 10 to the 7 meters. Meters per second, right? So this length will be equal to u times t, but the length is given to us as 7.5 centimeters, right? So we can solve for t to find for how long the electrons were inside these metal plates. So t is simply 7.5 times 10 to the negative 2 meters, the length of the plates, over the velocity, which is 1.73 times 10 to the 7. And the horizontal velocity doesn't change, okay? This velocity will not change in the x-axis because there is no acceleration in the x-axis. The acceleration is only in the y-axis, okay? So the time is 4.34 milliseconds. Nanoseconds, I'm sorry. Okay, and we are finally ready to calculate the deflection. So the deflection is due to the electrons moving in this direction, okay? So we want to calculate this y. And y will simply be 1/2 at squared. By the way, I want to make a correction here. This should be y equal to 1/2 at squared, okay? Because there is no initial velocity in the y direction, right? Because in the y direction, the velocity is 0 initially, and then they start accelerating upwards, so they acquire a y component due to this electric field, okay? I hope this makes sense. So it's difficult to explain it on the iPad. It will be easier in the classroom. So if we plug numbers in, we basically have to plug this acceleration in and this time, and we get 0.028 meters. And that's the answer. Okay, and part 3. The electric field between the parallel metal plates is removed. A uniform magnetic field is applied to deflect the electron beam into a circular path of radius 3.5 centimeters. Assess whether this gives a value for E over m in agreement with the standard value. And we are given the magnetic flux density. Okay. We basically have to use the fact that if a magnetic field is applied, we will have a force QVB on the electrons, which will play the role of a centripetal force. So mv squared over r. Okay. Now the Q is E. V gets cancelled. So E over m, if we solve for that, will be mv over r b. And now, oops, the m is not there because we removed it, right? So, okay, so V will be 1.73 times 10 to the 7, right? Over the radius of 3.5 times 10 to the negative 2 meters. And then the B is 3 times 10 to the negative 3. And if we do this calculation, we will find let me see, 1.73 times 10 to the 7. I'm using my calculator right now. Over 3.5 times 10 to the negative 2 times 3 times 10 to the negative 3. We find 1.65 times 10 to the 11 coulombs per kilogram. The accepted value is E over m equal to 1.76 times 10 to the 11 coulombs per kilogram. And you find this by simply using E as 1.6 times 10 to the negative 19 over 9.11 times 10 to the negative 31. And if you do that calculation, you find, let me verify because this is from my notes and I want to cross verify. Yes, so 1.76 times 10 to the 11 coulombs per kilogram. So it's close, but not that close, okay? And this is it. This was a really long paper. I don't know how people did. Let me know if you found this useful, and I will keep uploading solutions like this. Thanks for watching. Subscribe, tell your friends, let me know what you think, and so on. See you in the next one.